Yeah, thanks a lot for having me. Good morning, good afternoon, good evening, wherever you are. And again, this is, as Matt said, this is a tool where we present, this is a presentation where we present a tool, which is kind of uncommon because usually uncommon for me, because usually I give talks about how the methods, how the methodology behind these tools work. So we hardly give these kind of tool demonstrations, but we're going to give it a try. And of course, I'm going to sketch a little bit what is behind these tools, but we really want to do this presentation more on a user's perspective. And before I start, let me very quickly acknowledge my entire team who developed these tools over the past years, and particularly Stefan Hilmig and Lucas Burkholzer, who are majorly responsible for implementing most of the methods here at JKU. So what is the motivation? So to go in a little bit more detail, of course, there are lots of tools available. Why do we need yet another tool? Obviously, we have a particular focus, something we want to accomplish with our tools. And this focus is mainly motivated by exploiting design automation. So historically, I started working not on quantum computing, but on design automation for conventional circuits and systems, basically from everything from the controllers in the cars over general purpose processors and so far. And here, obviously, in the past decades, we developed very sophisticated design automation tools relying on SAT solvers, ALP, decision diagrams, backtracking methods. So we got very elaborated methods, and we've got them integrated into very elaborated and sophisticated design flows. And literally, those methods are one of the key reasons why we have the current situation where electronic systems are everywhere. And at the same time, when I started working in quantum computing for quite a while, but frequently I experienced that, okay, all those methods and into the sophisticated design flow we have for electronic systems and for conventional circuit systems, they allow the design of very complex systems. However, in many cases, tools for quantum computing don't really utilize or exploit these kind of methods so far. And this is sort of one of the main motivations. So I'm going to introduce today a couple of tools which have the dedicated goal of utilizing and exploiting design automation expertise for the domain of design and verification and simulation of quantum circuits. So that is sort of our main motivation and our main drive, basically. And in order to do that, I just would like to sketch a couple of key aspects what might be relevant in the design of this of quantum circuits. And one basically a core aspect is that, of course, if you want to have a tool which helps a designer in the domain of quantum computing, of course, at some point you have to think about how can you efficiently represent quantum logic. Of course, you can do that in terms of a quantum circuit, but in many tasks, you also need a very dedicated representation of the functionality. And here, the most straightforward way to do that is using matrices and vectors for operations and for states, respectively. And as you know, this basically yields the problem of that those matrices and vectors tend to be very complex. In fact, they have exponential memory requirement if done in a very straightforward fashion. And there are a couple of directions how to tackle that: tensor networks, matrix product states, and so on. But one particular technology, again, inspired from the classical design automation domain, are decision diagrams. And the main idea of a decision diagram is basically decomposing the respective description, in this case, the matrix, into submatrices like that. So you've got the top left submatrix here, the top right submatrix here, and so on. And then further analyzing these matrices, because what you can see here right now, that these two matrices here are identical, which means you can simply share them. And by this, you reduce the memory consumption. And then you can do things like, okay, you can actually multiply out common factors. So for example, you can simply say, okay, I have something like 1.5 and minus 1.5 here, and it simply depends. So what I can simply do, I can put them to these common factors onto the edges. And then in a similar fashion, I can do this here as well. And then suddenly, so I just took the -1 out here, I got this one here. And then suddenly I can see, look, now these two matrices became equivalent as well. So I can share them as well. And by keep doing things like that, and then also in a recursive fashion, further decomposing these matrices, I can exploit much more redundancies in these representations, and eventually end up with a representation of this matrix which looks like this rather than an exponential matrix. And in this case, in many instances, we are able to have a much more compact representation. And this is one of the core assets, the core methods in our tools, which we're going to use. And a particular good, sweet example where we can actually exploit that in a very nice fashion is, for example, in simulation, because here you basically have to represent the functionality in terms of a matrix and the input state in terms of a vector, and then you have to conduct a matrix vector multiplication. And the bottom line, of course, is that if done in a naive fashion, then you have this exponential blow up. While if you use the decision diagrams, as I just sketched beforehand, then you can do this in many cases in a much more efficient fashion. And this is one of the main ideas of utilizing conventional design automation expertise, namely decision diagrams, in the domain of quantum computing. And again, I said at the beginning, my goal is to have this as some sort of a user demo. So I would just like to very quickly illustrate you how easy these kind of tools can be used. So first, you just have to clone the GitHub repository, which is provided here with this URL, and then you have to compile the corresponding code, and then all you need to do is you need to write a Python script in which you simply include, for example, everything from Qiskit. So we are really developed our method so that they can work well, for example, with other frameworks like Qiskit. And then from our tool, you simply now import the corresponding implementations from our simulator, which is called the DSim here. Then you create a quantum circuit, either read in a Quasm file or create the circuit by yourself. You print it, and if I execute that here on a terminal, obviously what you get is you basically get the print of this circuit. And now that's now all our part. Now you can very easily integrate our simulator in it. You simply say, okay, look, what kind of provider, what kind of backend you want to use. We want to use this Quasm simulator provided by this decision diagram simulation package here. And then you simply execute the simulations on this circuit here. So you use the circuit together with our backend. You create, in this case, 100,000 simulation runs, and then you just get the result and print the result, and you basically get the results here. And obviously for a small circuit like that, probably any quantum circuit simulator would be rather efficient. But if you try that out for larger circuits, we have many instances where our method based on decision diagrams performs substantially faster than, for example, the Qiskit or original simulator. And on the other side, we also have the other way around. So we often also have instances where our solution tanks and Qiskit does quite well. So long story short, what we developed here and what we're providing here is a complementary approach, which in many cases is significantly better than other simulators, but also vice versa. So this is sort of the one example of how to utilize design automation in a quantum computing toolkit. Another example, again, where design automation can be used quite nicely is compilation or steps of the compilation process. Here, particularly, I would like to briefly sketch the mapping process or translation process. Basically, the step where we have a quantum circuit, you want to realize that on a particular target device. And then, of course, you have to map the corresponding logic qubits to the physical qubits of the device, and you have to satisfy all those coupling constraints. And in a naive approach, you can simply do a particular mapping here, and then sometimes you have to add swap gates in order to arrange it out. And then the typical design problem which comes up at this point is that you now need to optimize that with respect to the number of swap gates. So you want to minimize the number of swap gates in this particular step here. And this is a very hard problem, has been proven NP complete. But at the same time, this is a kind of a standard combinatorial problem for which many electronic design automation methods exist. In fact, this particular mapping problem here is very similar to a place and route problem we can see in electronic circuits and conventional circuits. So it is kind of a problem which has certain characteristics which we already have seen in the past decades quite a lot, and for which very sophisticated methods have been implemented in the past. And utilizing this expertise can also help here in this domain for this particular scenario. And our tools provides a couple of corresponding solutions. One is based on an A-star search approach. Another is using SAT solvers, so reasoning engines, in order to solve the problem in an exact fashion. And again, I don't want to step into the details here, but I find that very interesting, and this is sort of what motivates us a lot, is that you really can utilize these methods. And again, in this talk, I mainly want to focus on how you can use it. Again, all these methods have been implemented. This is the link again. And again, just a small Python script helps you to utilize that and to exploit that by simply importing corresponding libraries. In this case, our software is called QMap, Quantum Mapper. And again, you sort of initialize a circuit, a typical thing, what you would do in how you would do it in Qiskit. And then if you print that, that's what you get. And now all you have to do is within this Qiskit environment and framework, you first define what kind of architecture you want to map this circuit on. In this case, we decided for the Pagoda architecture, which kind of looks like that. And then you basically load our method we developed, in this case, the exact method, and you call the compile one with exact, which is now supposed to compile this circuit for the architecture we initialized before with our exact method. Then you get basically the result, the corresponding circuit, which is now mapped. You transfer the respective data structure accordingly so that you can print the circuit, and then you get the result where this now is your mapped circuit. You see one swap gate is needed, and since we used the exact method, this is indeed the optimal circuit. So just a couple of clicks away, or a couple of lines of code away to actually use that. Last, but certainly not least, another example of our toolkit, what we addressed is the problem of verification. We heard a lot about verification in the previous talks. Here we consider one particular, maybe still a kind of niche question. So namely the question of how to make sure that your compiled circuit indeed realizes the desired quantum algorithm. So what's the situation? You have your originally given quantum algorithm, then you put it through the corresponding compilation steps. After all, you get your resulting circuit, which satisfies, for example, which is composed of elementary gates only, which satisfies all your coupling constraints, and so on and so forth, so far. And as you know, in tools like Qiskit, you have several steps within this compilation flow. And then at the end of the day, you may wonder, is your resulting circuit still functionally equivalent to what you originally inputted in there? So this is something in the conventional, which is known in the conventional domain as equivalence checking. Here you can say something like this is some sort of question with which you want to verify whether or not your compilation result is correct. And also here, a couple of EDA solutions, design automation solutions, can help. In fact, the decision diagrams I mentioned before are a good starting point, because these decision diagrams, of course, can be used to represent the original quantum functionality as well as the compiled quantum circuit result. And at the same time, these decision diagrams have the nice characteristic that they are canonical. That means the function representation, if both function representations represent the same functionality, then both decision diagrams should be identical as well. So basically, you can simply build up the corresponding decision diagrams and compare whether or not they are equivalent, which is on its own already an interesting utilization of design automation work, because I already introduced decision diagrams before. You just use them as a black box, and by this you can solve this verification problem here. But actually, there's more, and this is something what also nicely illustrates on the one hand side how you can use design automation methods, and at the same time how you can further extend upon them. In fact, one particular characteristic in this in quantum computing is that quantum computing also is inherently reversible. So with this in mind, what you could do is you could take your original quantum algorithm as well as the inverse of your compiled results. And the inverse of any quantum circuit can be generated very quickly, because you simply change the order of the gates and reverse the functionality of each single gate. And if you have that, then what you can do is you can multiply your original algorithm together with the inverse of the resulting algorithm. And if both are functionally equivalent, then obviously this should yield the identity, because you computed something and then you uncomputed something. And if, again, the compilation result is functional equivalent, then you should get the identity. And this alone is not is a nice characteristic, but this alone does not help a lot. But in combination with decision diagrams, this could be really interesting, because if you do the same multiplication on decision diagrams, of course, you're also supposed to get the identity, and this is the sweet thing, the identity is a particular functionality which can be represented in a very compact fashion using decision diagrams. That means if you conduct this multiplication here in a very clever fashion, you can actually verify your compilation result while at the same time always remaining very close to this identity. And by this, it's not always working out perfectly, but if you do it in a really clever fashion, then you can actually conduct the verification while doing this whole process, keeping the representation linear with respect to the memory requirements. And this actually allows you to verify results of entire compilation flows in literally no time if you do it in this clever fashion. And this is also a very nice example of how design automation can actually help. What does it mean from a user perspective? Again, if you want to use something like that, you simply download the corresponding tool, you import the corresponding libraries. And then in this example here, what we put together is we basically took one quantum circuit, as we have done in the past examples as well. If you run that, you get your quantum circuit. And now we are going to compile this quantum circuit using the Qiskit backends, basically. So we're going to compile it to this architecture backend here with an optimization level of 2. Then we've got a new circuit, this mapped circuit here, which is now supposed to be equivalent to our original circuit. And in order to prove that, this is how the compiled circuit looks like. And in order to verify now whether or not the original circuit and the mapped circuits are functional equivalent, we simply take our QCEC, that stands for quantum computing equivalence checking method. We configure that correspondingly. We have a dedicated strategy of our verifier, which is optimized for the compilation flow of Qiskit. And then you simply run the verifier, so our method we provide, and this takes the circuit as well as the mapped circuit and the configuration, and then this automatically checks in the push button fashion whether or not those two circuits are functionally equivalent, and this would be the result which simply confirms that indeed in this particular case the compilation flow produced a correct result. And something what we believe could be a very important task and feature in upcoming design flows for quantum computing. Just as an example, in the conventional realm, doing equivalence checking, doing model checking is right now a huge thing. Often it requires more time to verify the correctness of a conventional circuit than actually designing it. And we believe that with quantum computing, we will see a similar development in the future as well. So long story short, a couple of tools we develop, again, with the focus on utilizing exporting design automation. What I briefly sketched here was basically that we have tools which try to represent quantum functionality or quantum states in an efficient fashion. We utilize that for simulation. We showed how we can use search methods or reasoning engines for compilation. We illustrate a little bit how verification can be used for that. And all those tools are publicly available on our GitHub and ready to use, as I illustrated with these brief examples. Another tool, just to mention that if you don't want to clone a repository and want to compile everything, what you could also do if you want to do a quick and dirty tryout, you can also access this web page here, which offers the simulation tool and the verification tool as a web front-end tool with no need for any installation, and also illustrates a little bit. It's a visualization tool which also illustrates a little bit how these decision diagrams are introduced, how they look like while you, for example, simulating through a particular quantum code or quantum circuit, basically. So also this is an opportunity to try out these tools. And again, this whole thing is a little bit with the aim of showing you guys how methods from the conventional domain of design automation, like decision diagrams, how they can be utilized, and this visualization tool is one of the other examples. So my timer here says I have half a minute left, and I would like to use this half a minute for, I hope you don't mind, for a shameless plug. All the developments we are doing here at the University of Linz are developments which are part of a research project, of a rather large research project funded by the European Research Council, and which is a rather huge project. When we just got funding confirmed in order to actually elaborate further on those developments. And for this, we are looking for PhD students and postdocs. So please don't mind this shameless plug here. But if you're interested, or if you know someone who would be interested joining our team or working in these kind of tool developments, let me know. With this, thanks a lot for the attention. And of course, I'm happy to address any questions. Thanks a lot.